you. Can you hear me well? Yes. Okay. So I'm Clément Bernard, and today I'm going to talk about RNA and torsional angles from RNA and using language models. And so it's part of my thesis, which is supervised by Faiza Tahi and co-supervised by Guillaume Postic and Sarah Ganet from France, I would say. And so RNA are molecules which are involved in multiple biological processes. And so there is an interest in knowing its 3D structures. And we also know that there is a link between its biological function and its 3D structure. And so the prediction of RNA 3D structure has been a challenge for years. And so there has been the recent release of AlphaFold3, which works also for DNA, for RNA. And so it uses some diffusion-based model, and okay. But it also has, even if it has changed the impact of the MSA in its model, it still has this multiple sequence alignment inside the model, which might be a bottleneck for RNA, as they have a lot of unknown families for RNA. And so the goal of my work is, given a sequence, can we train a deep learning model to just infer some structural features and then maybe later go back to the 3D structure, but just start with some structural features. And so for RNA, there is also the same in proteins. There are some torsional angles, but for RNA, we have multiple torsional angles. We have 7 of them. And there are also some approximation, which are pseudo-torsional angles. But anyway, the goal is to just have a more natural description for instance, for chemical description of the nucleotide. So given nucleotide, you will get some torsional angles, which will be defined depending on the atoms. And they can also be used for the quality assessment of RNA structures. And we will see it later on. And then you have some language models. So given a sequence, they will try to have a transformer-based model that will mask some input and try to predict the masking tokens. And so it will enable to have an embedding of the sequence-only representation of the RNA, and it can be trained to fine-tuned to infer some structural features. And so I've tried 2 models. There is one which is based on RNA-TorsionBERT, which is like a BERT style used on the DNA sequences, and we can just slightly change one nucleotide so that it can be converted into RNA. And it also uses some K-mer representation, and so the fine-tuning and the pre-training using some masking K-mer objective. And I have also tried another one, which is RNA-BERT, which is the equivalent of BERT, but for RNA, which has been trained on RNA central. And it has also been tested on 2 tasks, which is the structural alignment and also some clustering, but it has not been trained for torsional angles prediction. And so the goal of my work is, given a sequence, try to use some language model to try to infer the torsional angles of RNA. So for each sequence, so each nucleotide gets like all the torsional angles, so the cosine and the sine of the torsional angles, and using either the RNA-BERT or RNA-BERT. And so this is the architecture that we have. So given a sequence, we'll try to convert it into tokens for the model. So here the best method was with RNA-BERT. And then we had some layers to then try to predict the cosine and sine values of each of the torsional angles, and also the pseudo-torsional angles. And then we can go back to the angles at the end. And so in terms of benchmark, we tried with one known model for the torsional angle task, which is SpotRNA-1D. And it's a convolutional neural network and a residual, which given a sequence, try to predict the torsional angles. And it uses the one-hot encoding as input. And we also try to compare to AlphaFold3. So not directly the AlphaFold3 because it doesn't predict the torsional angles, but we infer the torsional angles from the prediction of AlphaFold3. And we just keep in mind that the AlphaFold3 uses MSA, which is not the case for either SpotRNA-1D or RNA-TorsionBERT. And so in terms of dataset, we use some PDB, some RNA from the PDB, and we ensure that there is a sequence dissimilarity with the validation set, which was from SpotRNA-1D, and the test set from RNA-Puzzle and CASP-RNA, which are the general test set of for RNA structure validation. test, I would say. And in terms of the evaluation criteria, so as we are dealing with angles which are periodic, we cannot just take the mean average error or the square error, I would say. So we try to compute it in terms of mean of circular quantities, which is a known matrix to compare structures in terms of angles. And so we use that metric to assess the quality of our method. And so here we have the result in terms of sequence lengths for the test set. And we have the MCQ, which is the deviation per angle. So it gives you an angle deviation, so around 20 degrees, for instance. And so we compare with spot RNA-1D in green and with alpha-4-3 in red. And so we see that we always do better than spot RNA-1D. And we are quite competitive with the infer angles from alpha-4-3. Whereas we do slightly better with structure higher than 200 nucleotides, and so without any multiple sequence alignment. And so now, can we use this model to try to infer some reference-free structural quality assessment? So in fact, given two structures, we can get a quality assessment of that structure. So given a prediction and a native structure, we can have a look at, is it close to the native structure or not? And so we can use the distance-based metric, which will be root mean square deviation, TM score, LDDT, etc., etc. Or we can also use the torsional-based metrics, which are the MCQ, as I presented just before, and with also the LCSTA, which are kind of the longest continuous segment with the MCQ threshold. And so given those metrics, so given one prediction and given one native structure, so if we take a look at the MCQ, what it does, it will extract the torsional angles from the predictive structure and from the native structure, and it will compute the deviation in terms of angles. And it requires to have a native structure. But then we can maybe replace the native structure by the prediction of our model. And so given a predictive structure, we'll extract the sequence and then feed it into a neural network that predicts the torsional angles. And so it will be like the real values, but like inferred by our model. And then we'll compare it to the infer angles from the structure. And so it becomes not a metric, but a quality-free assessment or like a scoring function. And like the scoring function, the idea is to, given generated structures, try to rank those structures given the quality of that molecule. And so the idea is to give a score of nativity-like, and the goal is not to have the reference, but just try to rank them without any reference. And so this is what we have with TorsionBERT MCQ, as I call it. And so in terms of benchmark, to assess the quality of that scoring function, we use some knowledge-based and some deep learning approaches. And so, for instance, deep learning approaches, they will try to replicate the root mean square deviation, for instance. And for a case, we try to replicate the torsional-based MCQ. And so to assess the quality or the link between the different scoring function and metric, we can compute the Pearson correlation coefficient, where the goal is to see, given one metric, so let's say the MCQ, and given our scoring function, how is it linked to each other? And so to do that, we need to have a different data set. So we need to have data set of decoys, where decoys are near native structures. And so we use 4 of them, one which with a very near native structure, the test set 1. And for 85 RNA, you have 500 decoys. There is another one with 20 RNA and 40 decoys for each. And then you have some decoys from RNA puzzle and also CASP RNA. And so here we can see the Pearson correlation between the MCQ and the LCSTA with different thresholds, so which are some torsional-based metrics. And you can see for each of the scoring function, like the link that they have with those metrics. And so you can see that the TBMCQ, which is the related scoring function that we developed, has the highest correlation with the torsional-based MCQ, and also with some LCS, but with a high threshold, with a 20 degree or 25 degree threshold, which might be linked with the quality of our prediction for the different torsional angles. Like we have deviation around 15 degrees, so or a little more, so it makes sense that we have higher correlation with higher threshold of LCS. And so as a conclusion, we leverage language models, or at least 2 language models, to infer some structural features from sequence only. And we got some comparative results with AlphaFold3 and achieved some slightly better with sequences higher than 200 nucleotides. But we didn't use any multiple sequence alignment as input. And we also try to infer some scoring function given those prediction of torsional angles, which enables the ranking of the structure is in torsional space. And as a future step, so can we go from torsional angle to 3D? And in fact, we can. Given in the AlphaFold2 architecture, there was the frame prediction and also the torsional angles reconstruction that was done to get to coarse-grained representation into full atom structure. And so we can do the same with RNA torsional angles. So given 3 points, you can get a 4th point with the bond length, bond angle, and torsional angles. And so you can reconstruct that structure with those torsional angles, where we try to do it. But in fact, this is some kind of result that we get using only the torsional angles. But in fact, if we use only torsional angles, a very small deviation in one step can just lose the structure. And also the reconstruction is sequential, so one small error at the beginning can propagate throughout the structure. And so we need more distance-based information to try to reconstruct that structure. And the same goes for the scoring function. So we compare to torsional-based metrics, but in fact, it is not well correlated to root mean square deviation, LDDD, TM score, etc. And so we need more information, more distance-based information to try to improve both scoring function and also the RNA-TorsionBERT method. And so all of our teamwork is available in the Every RNA platform if you want to have a look. And so thank you for your attention.
Thank you. Questions?
Hi, thank you. Truly fascinating talk. So you mentioned that you compared the predictions to AlphaFold3, but based on the Cas16 results, AlphaFold3 is not the best model for nucleic acids. There's other models like V-Fold that can substantially outperform AlphaFold3. We compared to these predictions.
Yes, in fact, here I just presented on AlphaFold3, but we did also a paper where we benchmarked a lot of state-of-the-art method, and we also compared to them. But at the end, like one of the benefits of AlphaFold3 when we did the comparison, it has the highest MCQ values compared to other state-of-the-art RNA-3G structure predictors, I would say. And so, yes, we did in the paper, there are comparison with like 10 other state-of-the-art methods, I would say, among them V-Fold or V-Fold pipeline, I think.
Thank you.
Any more questions?
Yeah, very nice talk. If I got it right, and maybe I got it wrong, you said AlphaFold3 would not predict torsion angles for RNA?
Not directly. Like it predicts the structures, and then from that structure we can infer the torsional angles. And in AlphaFold3 they use diffusion, and so there is no prediction of explicit torsional angles. In AlphaFold2 they did predict the torsional angles, but for proteins, not RNA.
I know, but then you have the atoms, and it's easy to calculate.
Yes, that's why we infer the structure, the torsionals from that structures.
Thanks for clarifying.
Yes, always.
Any more questions?
Yeah, thank you for the talk. So you, as the language models, you took like 2 BERT-like architectures, but for RNA, as of today, there are probably like dozens of other language models. Have you also compared with them?
Yes, that's work that I'm doing right now, but in the paper there was not a lot of release of language model for RNA at that date.
Do you have any like preliminary results you can share?
For the moment, in fact, the work that I'm doing is trying to get to the 3D structures, and so I tried with torsional angles, but it didn't go well, and so I'm trying with other method, and the results are not really good for the moment, so I cannot conclude on that.
Any other questions?
thanks for the talk. I'm just was curious about, have you tried to train on DNA but transfer that on RNA? Because you might have more data available on DNA.
For the torsional angle task, no, we didn't try to like train on DNA.
Because
We only try to fine tune on the RNA data, but we use some DNA-based models.
Oh, the BERT you're saying.
Yeah, the DNA-BERT.
Okay, any more questions? All right, then thank you to our last speaker.
Thank you.